we're asked first of all for an equation for the reaction of 2-methyl butane with chlorine, and it specifies using molecular formula. So, I mean, 2-methyl butane, of course, is that, but if you write an equation with that or anything that shows the structure, you're just not going to get the marks because it says molecular formulae. So you've got to do what it says. And you can see it's got 5 carbons, so, and it's an alkane, so 2n plus 2, where n is 5, gives us C5H12, and that's the molecular formula that you've got to use. And it tells us that we are just putting one chlorine in because it actually gives us the formula of the product. So we get C5H11Cl, and of course to balance that you have to produce HCl as well. So make sure always that your equation's balanced, and that includes in organic reactions. So then in the next bit it asks us to spell out the mechanism of that reaction, still using molecular formulae. So this is one of these set piece mechanisms you've just got to make sure you've really learned thoroughly. So it's radical substitution. It didn't actually ask you to name it here, but that's what it is. And the first step in radical substitution is the initiation step. So you've got to learn these names. And what initiates it is the UV light, because remember the UV breaks open the chlorine molecule to give you 2 chlorine radicals, and you need, I think, to specify that it's the energy from the UV that makes that happen. So that's all there is in the initiation step. Secondly, you have propagation. So this is where the main part of the reaction actually happens. Okay, so initiation is just a kickstart. This is where the main reaction actually happens. And the thing to do is just to remember that these radicals do what they do by taking one atom out of the thing that they react with. That's generally the pattern in all these organic radical reactions. So that chlorine is going to take one atom out of the C5H12, specifically one hydrogen, to form HCl. And of course what that leaves is now C5H11 with the unpaired electron, so we get that. In the second phase of propagation, then that radical is now going to react, and again it's the same pattern. It takes one atom out of the thing it reacts with, which is now going to be the Cl2, to form C5H11Cl. Okay, so again, same pattern. One radical takes one atom out of the thing it reacts with to give you that product and leaves another radical behind. And then, of course, that feeds back into there in a chain reaction. Each one feeds the other one by providing the radical that's necessary. So you've got to get both of those reactions right for the propagation reaction. You can tell whether they're correct. I mean, you don't necessarily have to write this in, but you can tell whether you've got propagation right, because if you add the two together, let's do that. So C5H12 plus Cl dot goes to HCl plus C5H11 dot, and sorry, we're going to put everything on the left hand side, so we've got this plus Cl2. Okay, so that's all the left hand side things there. If we put all the right hand side things here, and then we look at what cancels. Well, the Cl dot cancels because it's on both sides. The C5H11 dot cancels because it's on both sides, and what we're left with is C5H12 plus chlorine goes to C5H11Cl plus HCl. In other words, we get the overall reaction, and that's what you must get. If you've got propagation right, the two steps should add up to give you the overall reaction equation. And in principle, that's all you need for the reaction to happen, but you need to also talk about termination, which is the reason basically that you have to keep the light on, because if termination didn't happen, once you kick-started the reaction, it would go through to completion. But termination is what stops the chain reaction in its tracks, and that happens if two radicals react with each other. So there are 3 possible termination steps, and generally you need to certainly give more than one of them, and ideally give all of them. So if 2 Cl dots react together, you get Cl2. if two C5H11 dots react together, then just add it up, you get C10H22. And if one of each react, then C5H11 dot plus Cl dot gives you C5H11Cl. And those three are the possible termination reactions. And the significance of those, as I say, is that it means you have to keep the light on, because after a short time the chain reaction will stop as a result of these, and so you then need to generate more radicals with the initiation step again. So part C asks us to figure out the formulae of all the possible products that we can get by putting one chlorine into that. It must be into that. There's no point putting any other isomers of C5H11Cl down here which aren't based on that carbon skeleton, because they couldn't be formed in this reaction. So again, make sure you keep track of what the question's about. That was your starting point. So all of your products are going to be based on that. And so the thing to do is, first of all, to get all the structural isomers by just going through systematically and seeing how many different ways you can put one chlorine into that. So if we start by putting one chlorine at that end, that would be one isomer, and then we can just go systematically through the molecule. We've got one hydrogen at this position which could be substituted, so that would give us another isomer, putting the chlorine there. You might be tempted, now you're on a roll, to do that and put another chlorine up there, but it's important to realize that this and that are the same thing. Okay, remember, these two methyl groups are attached to the same carbon, so whether you put a chlorine on that one or on that one, it's the same thing. If you rotate around this bond, they would just alternate positions anyway, so that's not a separate isomer, so don't fall into that trap. But we can put one here, and that gives us a third structural isomer, and indeed we can put one on the other end, and that's different again. So those are all the structural isomers, but the question does actually prompt us to look for stereoisomers as well. So stereoisomers, remember, means same structural formula but different arrangement in space. That can happen for EZ isomers if you have an alkene, but obviously this isn't an alkene, so definitely no EZ isomers. But it can happen if you have a chiral center, you can form optical isomers. So what you have to do is go through these and say, well, are there any chiral centers? And you can see that this first one does have a chiral center, which is formed here. It wasn't chiral to start with, because in the starting compound you had two methyl groups attached to that same carbon, so didn't have four groups that were different from each other. But it does now, because we've chlorinated one of them, so that's a chiral center, and that means it will have two optical isomers. This one is not chiral, because you've got two methyl groups the same, but this one is, because you've got a chiral center there again with four different groups around it. This one obviously isn't chiral, because the carbon there has two hydrogens on board as well as the chlorine. So we've got two with chiral centers, so each of those could form a pair of optical isomers. So we'll just illustrate that for one of them, but it's worth noting that you can get the pair of optical isomers for that one, and also for this one. And to draw those, you always have to draw tetrahedra properly with wedges and dashes. So practice drawing the tetrahedron. That's the shape. It should have one bond pointing up and the other three all angled downwards, like that, because the angles are bigger than 90 degrees. And then you draw its mirror image, like that, and that's going to give you the correct relationship. And then wherever the chiral center is, you can just put the four groups around here. So in this case we could have, say, CH3 at this position and H at that position, and then CH2, CH3, which is there at the top, and then CH2, Cl there. So that would be the 4 groups ranged around that chiral centre there, and then we just put these in their appropriate mirror image positions. So CH3 and H, and CH2Cl and CH2CH3. So that would be an example. You could do that for the other one as well, but I think once you've made the point, that would be enough. Always when you do that, if you're trying to explain the relationship between them, the thing to do is to use the phrase that they are non-superimposable mirror images, because that neatly describes what the relationship is between those two things. Okay, so actually there are 6 isomers altogether, 4 structural isomers there, but for 2 of those structural isomers you get a pair of optical isomers, so in fact 6 possible products from that reaction. In part D we have to figure out which one of these structural isomers, see it could be a pair of optical isomers, but which one of these could have reacted in order to produce this spectrum. So we've got to go carefully through the reaction and figure out what would have happened. So it tells us first of all that we took the sample and we treated it with aqueous sodium hydroxide. So that's a very important reaction of haloalkanes, and you should know that what happens there is just nucleophilic substitution. So OH minus attacks the haloalkane and basically substitutes OH for Cl. So what would happen is, in that first step, that wherever the chlorine is, you would have OH instead. So we can write the equation for that in terms of molecular formulae, just to remind you what's going on. So C5H11Cl plus sodium hydroxide will give you C5H11OH. That's the substitution of OH for Cl plus sodium chloride. Again, make sure you have a balanced equation. Don't forget to put the sodium chloride in. So then, the product of those are refluxed with aqueous acidic potassium dichromate, and we know that that will oxidize primary and secondary alcohols. It would oxidize primary alcohols under reflux to make carboxylic acid. It goes first to an aldehyde, but under reflux you would oxidize further and get a carboxylic acid. You would oxidize secondary alcohols, but only as far as the ketone stage, because you can't then oxidize any further with aqueous acidic dichromate. If there were a tertiary alcohol, there would be no reaction. You can't oxidize tertiary alcohols with aqueous acidic dichromate. So that was the point of giving us the infrared spectrum, because it lets us look for these things. If there were a carboxylic acid or a ketone, there would be a C double bond O peak. And the C double bond O peak is very obvious. It comes around 1700 wave numbers, which would be there. So there would be a great big peak there around 1700, and you can see there is no such thing. So you can report that there is no C double bond O peak. When you talk about infrared peaks, always quote the datasheet to give the correct range. Otherwise they don't necessarily believe you know what you're talking about. So no C double bond O peak, which would have been 1630 to 1820 wave numbers. And that tells you that there's no carboxylic acid or ketone. And that immediately says it can't have been a primary or secondary alcohol that was formed. It must have been a tertiary alcohol that was formed. We can confirm that by the fact that it's still an alcohol. If the alcohol group had reacted and been oxidized, then of course the alcohol OH peak would be missing. But you can see it's still here. So this characteristic shape is an alcohol OH. Make sure you don't mistake it for carboxylic acid. Carboxylic acid is a much broader peak coming all the way down here like that. And completely smothering the CH peak. If you can see a clear CH peak separate from the alcohol peak there, then that's clearly distinguishable. So if we follow the numbers, it's about 3,200 to 3,600 wave numbers, which fits for an alcohol OH peak. So we can mention that as well. So the alcohol OH was not oxidized, which again supports the fact that it was a tertiary alcohol. So now we have all the evidence we need that the alcohol produced by this reaction is a tertiary one, and therefore it must have come from a tertiary haloalkane, and the only one of these that's tertiary is that one. Okay, and therefore that's the right answer.